So I cut this chapter into 2 parts. So we're going to continue with the part 2. So here you can see your long range indicators, and they are reliable when you use it properly. So the use of long range indicators, so here in this example, we're going to use indicator to control tool travel in order to hold close dimension shown right here. So in this example, it's just trying to show you the round thing that happened here being used to measure. So here you can see this part is right here, okay, not this one. So this is 0 indicator with 2 at first shoulder. And here is your stop cut at reading 6.0015, okay? So if the indicator has 2% full scale accuracy, so the part feature produced may vary from 5.8815 to 6.1215. This is just showing you, okay, for 2% full accuracy range right there that it can be able to read. Right being like this on this site that we're doing the right thing, so being used to compare. So here your 0 indicator on gauge block, okay. So this I have little 6.0015 gauge block there. We're going to stop cut at 0 reading. So even if indicator has 2% full scale accuracy, the part feature, okay, will be the desired 6.0015 if we use, okay, long range indicator properly by using the gauge block standard before you measure the part. So we give you a really good accuracy. If you don't use the gauge standard properly, you're going to get your range right there, meaning like you have errors in between them, okay? You can't be able to get the correct measurement. So counterclockwise dial indicators, you can see right here, we have clockwise going to the right and then counterclockwise going to the left. So continuous dials read in either direction. So there are 2 continuous dial, clockwise and anti-clockwise. So clockwise is like that, and counterclockwise is going this way. They're just showing you here the measure point. This is your reference point, and these are your parts. Okay, so we touch here at the contact point, and here you have a change in the height with the standard and the rear part. So anyway, measuring the little change right there. So when you touch it, we get the difference right there. Okay, so here first standard, and then the part. This is your change. And here it's just showing you the comparison between the clockwise and the counterclockwise. So here the first measure point. Your counterclockwise is going to measure the inside part. For clockwise, you can start from here. Okay. Also, you can start from here. And here we can read the change. This one is a little bit difficult for you to be able to see because we're measuring on a different part, okay? Putting it, this part, actually putting it that way, okay? You can see that. And again, you don't have to worry about reading. It's more like a knowledge check here in this chapter. So if you can remember, we have 2 counterclockwise and clockwise continuous dials, then you're okay. Indicator range. So in this picture, just showing you the time analogy, and we use it to state hand position. Okay, so most indicators have a working range of 2.5 tons. So here we have 9 o'clock, we have 12 o'clock, we have 3 o'clock, and then we have 6 o'clock. Okay, hand position. Because dial phases, they vary, so the time analogy is used to state the hand position. So range is independent of die size or discrimination. It's a function, okay, of your amplification. So range is not affected by the direction of your rotation. So to achieve the greater range or accuracy, we can use both large or small, okay, dial indicators. Selection of a die indicator, how we're going to select, we're going to follow this. So we consider functional and metrological performance factors. So when we select the die indicator, so these factors are interconnected like that. So if you look at the comparative performance factors, what we wanted is the measurement with reliability, then the measurement consists of, and going on 3 different ways. If you want to go discrimination, you go resulting from amplification, resulting from mechanical design, okay, and then your instrument design. So if we're looking for the measurement consists of range, we go the same path, okay. We're looking for the precision, we're gonna go this path, okay. For discrimination, range, and precision, when we select the die indicator, it's always pointing to your inherent instrument design. For reliability, we have reliability, repeatability, and accuracy. So go this flow, okay, you can get a result from resolution. You can get the readability. I think I misread that. Yeah, so for reliability, we have readability, repeatability, and accuracy. So for readability, we're gonna go resolution or other readable factors. And then go down based on your design again, and then your instrument design. If you want repeatability or accuracy, okay, proved by calibration, and then it's going to go all the way down to instrument use, okay. So that's how we flow when we want to select the die indicator. So the die indicator ranges shown right here in 1035 table. So a special selection method is used for die indicators to ensure a practical selection for most measurement requirements. So die indicator ranges, you have number, range, B and C right there. That's just showing you the range. So here C 0 to 100, blah blah blah. And then cluster precision instrument, the same thing. Okay. This side is for your balance for that, and then CC is for your continuous dials. So based on 2.5 tons range, same for all dial sizes, and same for counterclockwise rotation. So see, we also have to look at the manufacturer's catalogs for ranges, okay, of long travel type. So every instrument always comes with your certificate or the calibration sheet, okay, or you have a catalog or manual, so you always look for that in order for you to be able to determine these ranges. So here the indicator selection. Here's your hand, and here's your standard 0.0005. That's your graduation going that way. So 12 divisions on that, 2 divisions going 0.001. Okay. So you just go with that for each graduation. So you can be able to calculate it either way, going to the left or to the right. To the right plus, to the left minus. Again, each increment is 0.0005. Okay. And you can do the math. So discrimination, approximately 10% of tolerance for this case. So total tolerance should cover about 10 divisions. Yet your range is a total tolerance more than 10% of dial and less than 25% of dial. And your readability, select largest dial that satisfy A and B and physically meet the requirements. Okay. And again, you only have to concentrate, okay, your plus and minus signs and how it's rotating. You have to know how to read this, okay, the one that is at the center, and that's your graduation mark, okay. And if you can do that, you're fine. Okay, so effective indicator errors cause bad parts, okay. To be accepted, you're supposed to be getting rid of bad parts, but you might be accepting them if you have indicator errors. And then you might reject the good parts if you have indicator errors. And that belongs to your production inspection. So the effect of indicator error, bad parts that will be passed as good. Okay, so here you can see your error that's designated tolerances plus or minus 0.0025. We're actually at 0.0001 inches for each graduation. So good parts that will be rejected is going from here to here. Okay, and bad parts that would be passed good from here all the way to there. And then this is just your designated tolerance that you can play. And they are all errors. Okay. Use of dial indicators. They're frequently built into other measurement instruments for readout. So they are reliable when treated as special forms of comparators rather than as direct measurement instruments. Meaning like you can use it with other instrument readouts. Just like the vernier, okay, amplification that you can use with your calipers, so you got vernier calipers. And here's your do and don'ts for indicator use. So when making comparison measurements, it's totally advised to you to take precautions. Rigidity is important to the proper use of dial indicator. We don't want rigidity, okay? So do properly design the clamps are available, use them, check frequently, okay, for play, check if your instrument is a mess up or not, and then set it back to its series setting. So use ample supports and keep them as short as possible. Okay, we have support. I've got one in my office, I'll show you. And you have to keep that support at a good height, okay? And you want to make it as short as possible. And use reference surface whose features are known in calibration, okay? You have to use a reference surface again, not with any kind of part. You have to use the features that has been known and also in calibration. Clamp to the indicator back whenever it's possible, okay? So make sure that it's completely stand and this isn't loose. Don't a makeshift clamping causes a shift, okay, that destroys the accuracy and makes setups difficult. As you can see, your instrument is completely, okay, is held by this stand. So therefore, this clamp got to be sold. Okay, you should be very careful with this clamp in order for us to be able to have accuracy by using this instrument to measure. Okay, the part. The slim poles and arms do not provide sufficient support. They're not very good, so don't use it. And do not use odds and ends for supporting reference surfaces. Okay, we don't want the odds and we don't want the ends. Do not clamp to indicator stem unless adapter is used. Definitely have to use your adapter. So this is just trying to show you the rigidity, okay, the importance of rigidity using a standard indicator and accessory. So here we have a double right there, and this is my part, and we're measuring it, and you can be able to see the front view. This is showing you the 0.0001 indicator, and the second one is a 0.001 indicator. Okay. Calibration of dial indicators. You have to do calibration, so it is calibrated the same as other instruments. So we're going to use gauge blocks again, okay, to calibrate the dial indicators. Accessories and attachments. So here is your contact point, okay, for the dial indicators. So the dial indicators, they're very versatile instruments because they have different interchangeable contact points. And we can use them in many different measurement situations. So here you have A is your standard point, and here your contact point is tapered point, button, regular, flat. And you also have a button type, flat, and then wide face, flat point. Here's your screwdriver contact points. Okay, they have different shapes, like just like that. Your pros and cons of flat contact points. So here, flat contact points, setting standard. That's your part. and here is your dial indicator contact point at the tip of that. And here again, standard, and then here is your part, flat contact points. Another satin standard, and here is your part. So for most measurement, not reliable closer than if you go 0.0001 inch because of varying air, and then also your oil film. So least reliable when 0, okay, on a flat surface because of, again, air can be in there on that flat and absence of, again, film on cylinder, okay, because you're measuring like this one is totally a cylinder part, and this standard is a square, okay, almost square. Spherical contacts usually provide greater reliability than flat contacts, okay. So here we are using the spherical one, and thus with better reliability and at very high amplifications, okay. With heavy gauging force, they present problems though, okay. So even though they're good for reliability. So those are spherical contact points. So point contact or spherical contact should rupture air and oil film on flat surface. Same with flat standard and a flat part. So we're just talking about this little gap right there, okay? Not reliable spear to spear contact. Here, spear to spear contact makes high point difficult to find. So out of line measurement from failure to pass cylinder under contact measures, okay, called instead of diameter. So here you can see that's your spear to spear contact. We're going to exclude the measurement of balls. A spherical contact usually provides greater, again, reliability than the flat contacts. So at very high amplification, however, or with heavy gauging force, they present problems. Spherical, okay? A sphere presents a problem even to a flat contact point. So here, your part is sphere, and we have flat contact, and we have sphere contact. So that's your spherical measurement. So a cylinder, okay, presents a line contact with a point contact of the contact point, and the diameter of the cylinder must at some time be in excess, okay, of the contact point. I'm just trying to tell you how difficult it is to have a sphere to sphere, okay, contact. Here, spherical contact point. The sphere represents a contact, and the center line again of the sphere may cross the axis of the contact point. So here the center line is right there. It's supposed to be right here, but it can come off, okay, from that line. Cylinder will act against the lowest point, okay, even if a flat contact is not square. This is not very square flat contact. It is a flat contact, but it's kind of serrated. And here are flat contact points. Okay, a sphere may pass to one side of the lowest point. Indicator stand looks like that. So that's your indicator, and this is your indicator stand. That's your indicator stand, and you can hold indicator with that. So here the accuracy of the measurement depends on much on the positional relationship, okay, as upon the indicator. So therefore the indicator stands are useful for this reason. So when we use an indicator stand on a reference surface, we call it a test stand. So these indicator stands permit, again, adjustment in all three axes, your X, your Y, and your Z. So this gives them both versatility and reliable positioning. Okay, so here when we attach a reference surface to a dial, it is known as comparator. So here you have your dial right there, okay, and now we are going to attach, okay, a reference surface. So in that point we call that comparator. So we have three axes, constructed through a test stand with movements and measurements. So movements, your x-axis, your y-axis, and then your z-axis. So these are all your movements and measurements that you can go. And here is your rotational movements, and this is translational movement. Okay, your physics again. Translation going that way, rotation, rotating. Translation, okay. This is rotation. So the adjustments of the test stand, okay, this guy, allow the indicator to have 6 degrees of freedom because we have 3 axes, okay, therefore you have 6 degrees of freedom. So the part and the indicator must be positioned, and then you must constrain them to make an accurate measurement. So there's only 1 degree, okay, of freedom remaining. So that's, you got to get it in your setup. So both the power and the indicator must be constrained. Okay, from all x and y movement, we don't want x and y to get rid of it. And their z-axis brought in line. So the indicator then measure movement along the z-axis only. So if x, half of your z-axis, by the way, so if x of the bar is not z of the indicator, the measurement is not going to be accurate. Okay. So as shown in the right, this is not accurate. See how it's all messed up here? It's supposed to be like this. A rotation around any one of 4 separate x and y axes will destroy the accuracy of the measurement. Here, your y axis, and here, your x axis. Okay, your z axis is the one which is very important, and we want only that movement. Now we're trying to get rid of this too. Movements and degree of freedom. So all elements must be considered. So here's your reference surface, and this is your part, and that's your standard. In comparator, so the reference surface is attached to the stand, so thereby it becomes part of it. So any unneeded movement, even if provided with a lock, is a potential source. Okay. So meaning like we don't want even if you have a lock here, you will definitely get the error, okay? Because it will give you unneeded movement. The kinematic consideration require that all movement within the instrument and stands be considered except along the z-axis. So dial comparator, you have your functional, then you have your metrological features. So the dial comparator has a general C shape, okay, of all the outside diameter instruments. So every time you do measurement, you have to consider, okay, all the movement within that instrument and the stand, okay? And you definitely need to constrain in order to keep accuracy. The platen, the angle or table must precisely square to the z-axis. That's the line of measurement for dial indicator. So serious error can result from a lack of squareness. So here, kind of tilted there. Your x, okay, here, axis, and here is your y-axis. And this is your z, which is your axis of measurement. So the cosine errors, okay, those are your rotation errors caused by 1 degree applies only to the trouble of the indicator and figures out to an error in length of only 10 micro-inch. So note that the same misalignment, okay, with a vernier height gauge creates an error based on full length and would be 300 micro-inch. You don't have to worry about this. If you can be able to understand the serious error can result, okay, from a lack of squareness, and then you have to be careful with your z-axis because that is the line of measurement. Okay. After cosine error, we're going to get into sine error. So cosine error is the least of the errors, okay, caused by misalignment, even though this type of error gets the most attention. So cosine error is already shown in the previous slide. And the error is function of the radius of the contact surface. For sine error, okay, the sine of the angle, again, the sine of the angle caused by if you do not remember sine and cosine, you have to review your mathematics, okay, please. If you haven't taken calculus 1 and 2, you should do that. And if you want to understand what is cosine and sine, I'm going to throw maybe a supplement, okay, page later on for you to be able to read to review. So the sine of the angle caused by misalignment with a flat contact is a much more serious error than your cosine error. So because a misalignment micrometer, okay, or snap gauge will have this error at each contact surface. So again, if you don't know sine or cosine, just remember that in dial indicator, because it's rotating, okay, or tilting, you always have an angle. Every time you have an angle, you will have sine or cosine error, okay? And these angle, okay, happened because of your sloppiness or misalignment, okay, on the contact points. Alright, so the next one is your reliable comparison measurement with dial indicators. And just a little table here is showing you 1 all the way to 12, okay? What you need to know, and you may have noted a strong similarity among items in these checklist, and this emphasizes their importance. So the very first one is determine that this is best way to make the measurement, okay, for reliable comparison measurement by using dial indicators, because it's the best way to make the measurement. Second one is select a dial indicator with sufficient precision, okay, to spread the tolerance again over about 10 divisions, and with sufficient range to contain the tolerance in not more than 1/4 of your dial. I just trying to tell you to keep the range and the division straight. And then select the standards of suitable precision. Okay, you have to choose the right standard. Check calibration data for indicator and standard. You have to do always for any kind of measurement. Calibration matters. So select contact point indicator stand. Okay, and then the reference surface that will ensure the correct, again, alignment. Okay, alignment always give you a lot of errors, so make sure everything is aligned when you measure by using this dial indicators. Thoroughly clean part, instruments, and all other components of the setup. Cleaning is so important. So make sure you do the housekeeping. Make setup check, alignment check, security, rigidity of all points. Zero set indicator on the standard. Repeat until satisfied, okay, to make sure accuracy is there. So measure part with indicator and adjust with the value of the standard to provide measurement. And then you do it again, repeat. Recheck all above steps from 1 all the way to 9. And then consciously inquire into possible bias, and think about if you have done something, okay, that you're not supposed to be doing. And if it is a critical measurement, have someone else make the measurement so that you can be able to see your variance, okay, your measurement and the other measurement, and try to see the discrepancy. And if that discrepancy is greater than 10% of tolerance, okay, is warning that some step is not correct or not adequate. So you gotta check it again, yeah? Alright, so these are the suggestions for reliable use of dial indicators. Another table right here, so that's metrological data for your vernier instruments, and here is your reliability. So for general metrological information about dial indicators are shown right here. Okay, you only get the general metrological information. So here a practical comparison dial indicators cannot be made without considering the means of supporting the indicator. Okay, type of measurement, range, precision, discrimination, sensitivity, linearity. Okay, for reliability, practical tolerance, we take a look at it, especially for the professional measurement. Okay, and the practical manufacturing tolerance, we also look at that. Constructive use of errors. Error can be its own worst enemy, so be very careful. So here you can see square and comparator, okay, table to detect and correct the misalignment. So here is a comparator table, and you definitely don't want this kind of alignment, okay? So you've got to correct all these kinds of misalignment. Stationary reading means squareness has been attained. The movement is from high to low. The axis of movement is along the one square line that always exists. Okay? That is a stationary reading. Or it will create incredible amount of error from coming out from your misalignment. Calibration of dial indicator. So for calibration, okay, dial indicators we calibrate for its sensitivity, and also we calibrate for its accuracy. So calibration is done by running the indicator through its range using the micrometer head and noting any differences which are error. So that's what we're doing in calibration, checking error, okay, and making your instrument of making your instrument as good as standard, and make sure that it is reading the standard measurement. So this calibration method, frequency of calibration, okay, is quick and can be performed frequently. So that's your calibration of your indicator. And our indicator is pretty fast, so therefore you can do it. So here, frequency of calibration, but again, this type of calibration violate your 10-to-1 rule and give you the observation errors. Here, frequency of calibration, dial graduation, you have high, low, and then your laboratory environment. So we're doing 3, 1, 2, 3, 4 actually method, and then comparison to this, and that. Okay, there's a large strand micrometer and a rain gauge block, magnified large strand micrometer, and the point contact gauge block. And then you're going 6 to 9 times, okay? 3 to 6 times of checking, 1 to 3 times of checkings, 1 to 3 times of checkings, and that unit is again months. So the time can be days, week, or months, or even years, okay? 9 to 12, 4 to 9, 3 to 6, and 2 to 4 times. Again, your unit is months. So 12 months, 3 to 6 months, and 3 to 6 months for these methods. So therefore, the contact of the head, okay, should always be within the triangle formed by the point. So here, this is your contact, okay. That's just showing you the triangle formed by the points right there, 1 time, 2 time, and then 3 time contact. So the contact of the head should always be within the triangle formed by the points. So when it is near the line connecting the closest points, such as at A, bending is minimized. So for least bending, only one reference point is used, okay, as at C. So here you can see your contact triangle, and that's your contact point, and here is your cylindrical head, okay, and use 3 points support, 1, 2, 3. Now gauge head tip must fall within the triangle formed by 3 anvil points. Don't worry about any of it. This is just trying to tell you, okay, contact of the head should always be within the triangle formed by the points. So the contact of the head should be within the triangle formed by the points, okay? So accuracy calibration, this is the last one. It's nothing but we're seeking accuracy in calibration of your dial indicators, and accuracy is the measure of perfection. and uncertainty is a measure of error. So accuracy is the degree to which an observed value, agrees with a true value. So error is any deviation, and uncertainty is the maximum amount of error under standard conditions. So if you get each one of that, that'll be okay. Know that accuracy is a measure of perfection, and certainty is a measure of error. Accuracy is the degree, to which an observed value agrees with the true value. Error is any deviation of it. Uncertainty is the maximum amount, of error under standard condition. So if you think about uncertainty, think about error, okay? If you think about accuracy, think about standard. So that's your true value. You're always comparing, your observed value with a true value, your part with a standard. So that's for accuracy. Accuracy calibration of a dial indicator. So accuracy is important to the design. Remember the flow, when we select the indicators of design of the instrument. So therefore calibrate sensitivity first, in dial indicators calibration. So to calibrate a dial indicator, first you check a point at the beginning of the range, one at the end, and one or two in between. So that's how you calibrate. So for long range indicator, calibrate for sensitivity at the beginning of the travel end and in the usable range. Sensitivity range, pretty important in calibration. So then calibrate the portion of the range that produces usable readings for accuracy. Alright, that's it for chapter 10.